very warm welcome and very good evening to all. I welcome everyone for this first talk of our series, Talk with an Expert. Today we have Mr. Chetan Parmeshwar, Dr. Chetan Parmeshwar, who worked in various fields. And if I start giving his introduction about his education and his past experience, I think this talk will not be enough. Okay, so welcome, Dr. Chetan. Okay, today we are in fact at Dr. Chetan's home at Bangalore. So today we will be discussing about his experience at LIGO, followed by we will be having a live view through the telescope for Jupiter and Saturn. Then we will actually hear more from you rather than me talking, sir. Sure. Okay, so welcome to the talk. Thank you. The podium is yours. Followed by which I have list of questions which has been already posted by the viewers. Okay, so I will slowly start asking the questions. Sure. Yes. Good.
Bharat, thank you for having me here and giving me this opportunity to talk. As you know, astronomy is considered as the second oldest profession in the world.
Okay.
There have been astronomers, people have been amazed at looking up and wondering what's out there.
Okay.
And trying to understand and figure out what is going on.
Mm-hmm.
And then initially it started off with Earth in the center and everything else moving around. And then we also, later on, I think they found out that actually it was the solar system that, with the sun in the center and all the planets moving around, is what is the actual thing.
Correct.
And if you actually look at what the history of science and astronomy, we've been able to go only to the moon.
True.
And there's so many things we have had to explore, and there's so much more that we can learn from it.
Correct.
And now with the recent science that is heading into looking at exoplanets, where looking at where a lot of funding is being allotted to identify planets, what they call as development planets or Earth-like planets.
Okay.
So I think that's where the next future of science is going to be.
Mm-hmm.
So interesting things are happening in the field of astronomy. Interesting things will happen in the future too.
Mm-hmm.
Taking into history, I think Galileo developed a small telescope. And that's where it started. Man started peering into and looking at different objects much closer.
Mm-hmm.
And then different size telescopes were developed, different technologies were developed. For example, the telescope that we are using today is an optical telescope.
Okay.
And then there was the radio astronomy, which uses radio frequencies to identify objects. And then LIGO came along, which is a different technology where we detect a gravitational wave coming from either a binary star or a supernova explosion. And it is based on Einstein's general or the theory of relativity. So at LIGO, it was interesting that I got selected as a control systems engineer to build the complex control systems for LIGO itself.
Wow.
We, along with a few engineers, got together, and each LIGO station was built. There were two LIGO facilities. One was built in Washington State, US, and the other one was at Livingston, USA. And taking into the rotation of the Earth, the distance between them was such that about 3,300 miles or so, 3,130 miles. The event that occurred out of space would occur 10 milliseconds exactly at the different, could be detected at the different second LIGO station 10 milliseconds apart.
Okay.
And that was one of the way we would be able to know that it was from outer space.
Okay.
There was a local event because LIGO was so sensitive, we could even detect somebody flushing the toilet. So we also had issues with in Lucia. We had issues with train running bats and the tigers that try the raids down also being detected while we were trying to do. Okay. The interesting part about LIGO was initially when they proposed, the proposal was given for $300 million, the highest to the National Science Foundation, saying that the LIGO will be built by my colleagues Ray Weiss and Kip Thorne, who are the this year's Nobel Prize winners for physics. And they propose that they will not be able to detect anything with $300 million. And yet they were funded. Okay. That's the interesting part. They said maybe we will be able to detect one event, maybe one um, supernova explosion or a primary star merger or something like that. But they said we will not guarantee, we will not, but we need $300 million to fund. Okay. This is the first phase of it. Okay. But then LIGO has been able to detect much more than what they have thought. Okay. LIGO by itself is very unique kind of an instrument. They use a laser interferometer that's in the shape of a L. Mm-hmm. And there's two mirrors with 99.999% accuracy reflection on both sides of a 4 kilometer long tunnel. Okay. Hanging by a very thread. And so what happens is this is reflecting so the light goes in, reflects for almost a million times before a trickle comes out. So they call it as a light bucket. Oh, and the light that comes out, both of them, if they're at the same distance, the light that comes in is in phase. Okay. And then you get a fringe. And that's how they measure the distance of the thing to an accuracy of 10 to the power of minus 21 meters. Okay. So it is like 1 millionth of your diameter of a hair. Okay. That small distance of variation in the 4 kilometer length is what is being measured. And it's interesting that I got to work there, and it's really nice. And now the technology is used there. The first time it was built for such a long technology thing. As an engineer, I think I enjoyed very much. Okay. There were about 1,44,000 channels of data that we were monitoring at random. Okay. We had real-time computers, real-time operating systems. Interesting thing, for example, that for the 4 kilometer length, we had a computer on the other end monitoring that, controlling that one mirror. While we had the main mirror controlling computer on this end. For the light beam, the data to go through a fiber and come back. Okay. Took us 13 milliseconds to go and 13 milliseconds to come back. 26 milliseconds we had to control, get the feedback. Okay. And our operating system was timed so that it will actually work within that time frame to be able to control it. And we had real-time operating systems which were timed to actually do that control.
Superb, superb. That's a wonderful experience. I think if I actually look at the questions that people have asked me, and if I look, if I hear what are the brief description that you have given, I think I've answered almost all the questions. But however, I'll go first in detail about it. The first question goes like this: what technologies are available for observations of this type above and the universe?
A lot of things actually. I think initially it started with the optical telescope with Galileo.
Of course, with the Galileo.
Yeah. And then people thought, why not look into the wide spectrum that we have, starting from microwave. And they've done the microwave background, looking into the early universe.
You mean to say the proof of the Big Bang?
There's a proof of the Big Bang.
Exactly.
And then they were thinking the universe is continuously expanding, but they've also seen that it's coming to a slowly becoming stable. So that was a surprise with the Kobe microwave background. And then there's the radio frequency telescope. Very close to where I was working in Sapporo is the National Radio Astronomy, the biggest radio telescope array. And then the biggest radio telescope is in
Arecibo, yes.
And that is built on the ground with 300-meter diameter. And it's an interesting way concept of array. And then now people are looking into square kilometer arrays, SKAs, where they put multiple radio telescopes and then combine the image. Then there's gamma ray telescopes. And then there's also solar telescopes which just look at the solar radiation and solar things. So interesting things people have come up with, just not the optical band, but also other things.
So I think we started with 15x telescope and 15x, that is when Galileo started looking at Jupiter. It was 15x in terms of magnification. I think now we have moved to probably 15 millisecond, 15 arc seconds of differences can be notified. Yeah. So I think it's a predominant in past 400 years. I think astronomy is moved from the magnification of 12x to 18x to rather from visible to invisible band, and even the slightest of the slightest difference can be I think noted, and the details can be rectified.
Interestingly, if you see the history, the people who have funded most of the telescopes to be built and to understand the sky were the people who do it.
Okay.
Even in the US know the US United States National Observatory itself is there, and they've also funded various other observatories to be built and to understand the sky. So people who were in a ship and they were in the middle of the ocean, the only way they could know where they were located was look up in the sky on a particular day. Depending on the almanac, they could see where they were located in the sky, which way were they wanted to go to reach a certain they didn't have GPS at that time.
Correct.
And so Navy basically went and invented observatories to go and do research and to identify stars and planets and actually do a good map.
Okay.
And now, though GPS has stopped in the recent years, but for the last few centuries, people have come through ships and visited various continents and countries. They are dependent on stars and somebody reading the stars to navigate them in the night.
Correct, correct.
And so that's how your Navy, your National Research Lab, Naval Research Lab, even today has been funding observatories or telescope observatories.
Wonderful.
Even in Flagstaff, Arizona. Even the one that I worked in Magdalena Ridge Observatory was funded by Naval Research Lab.
Oh, very nice.
So the Interferometer project that I worked with was designed to actually increase the resolution and the depth of viewing for a telescope.
Okay.
But in a unique and a different way. So in the Magdalena Ridge Observatory that I did after LIGO, there were two projects. One came about as a fast tracking telescope to track satellites or missiles that were being sent from a different country or a rogue country.
Okay.
You know, telescopes are very slow moving things.
Correct.
And because the Earth itself is moving very slowly. And the funding came after the Columbia shuttle disaster.
Correct.
When the Kalpana Chawla's death and the blowing up of the shuttle, the time fell off, and then nobody noticed at that. Okay. So then there was thoughts about why don't we image as the shuttle flies, but there was no fast-moving telescope that could track the shuttle as it during its journey. Correct. And so the defense approached us and said, why don't we build a fast-tracking telescope? We could image the shuttle. We could also use it for anti-missile purpose because White Sands missile range was there in New Mexico. And so that's how Magdalena Ridge Observatory was born with that thought in mind. Okay. And then they also said, why don't we, the fast tracking telescope, it could also track fast moving objects like meteors or
space shuttles or
or even your International Space Station, things like that, that could be monitored.
I think with the help of this, you can even check. Recently, there was a asteroid or a meteoroid or a near Earth satellites or nearer objects, okay, an hour what they call. I think before they impact, probably an hour, the disaster management system.
Something India could be used for multiple purposes once the technology is put in place. And the thing with having a fast tracking telescope is to have a very good control system, so that you don't have any wobble or things like that when you put over position. So okay, it should have a very smooth control system. So electronics for that was really interesting. Okay. The other thing that I was personally involved with was the interferometer telescope. Okay. Telescopes in currently we have a 10-meter telescope in Hava. And then people are planning much next generation of telescopes. One is the 30-meter telescopes, Pvt, which is US is planning. And there is a giant Magdalena telescope, which is a 24-meter telescope. And then Europe is very ambitious on building a 42-meter diameter telescope. Okay. Which is the extreme ELT, which is the extremely large telescope. And these are going to be the future of telescopes. I think even India is also contributing towards the actuators, which for the TMT. For the TMT, yes. The interesting thing with when you go bigger and bigger, you know the atmosphere is not going to be flat and stable. Correct. And there's going to be density of the air, and it causes multiple wavefronts in the signal that you measure. So you want to correct for that. So you have actuators that will actually warp the mirrors to adjust to that wavefront by using something called as a feed-forward signal. Okay. And that's an interesting thing that comes up when you build bigger and bigger large telescopes. But just to clarify, the much bigger and bigger telescopes you build, it's still going to be hexagonal segments of 1 meter diameter or something, which you join to make that still parabola. Okay. And then you have control systems, much more complicated control systems to adjust the to ensure that you have a smooth surface. So basically, it's like playing with the mosaic or playing with the Lego kind of a system, so where you keep joining small blocks to come up with a big system or a big object or a big image. Making a bigger glass is very tough, and so you end up doing smaller ones. And that's where this interferometer school of thought came in. Is why not put smaller 1 meter diameter telescopes? Okay. And you put them in an array in the shape of a Y. Okay. And you can put these small telescopes along this Y at different lengths. And you can have a 400-meter diameter length of a Y. And so you can easily get a 400-meter diameter telescope. And you combine the light of all of this to form an image. Why was it specifically? Why not at 180 degrees apart from the axis? No, so you can get all the 360-degree coverage. Okay. So if you have a 360-degree plane, you divide it into three, you get 120-degree each. Correct. And so that would help us to monitor from the east to west as you rotate. The signal from one star is closer to this telescope, but it's farther from this telescope. The interesting thing is then you have to make them all come in phase, and so we have these vacuum delay lines with cards moving in as the day goes by to equalize the phase of all these lines. Okay. And then they're all brought into one small lens to combine them to make an image. And that's a very interesting thing because everything has to work in perfection to make that image from all the 10 telescopes to come in. So the interferometer idea itself is very brilliant. Okay. I think we are moving from probably a telescope which has an aperture of 2 inches. Yeah. To we are going for kilometers. So I think that's a very huge evolution in this past 400 years. Sure. And from visible to invisible, and probably a small variation in the light spectrum to a small variation in the wavelength. So that is a huge thing. And I never knew that. I always thought that the telescopes or the funding which is being given was majorly towards identifying exoplanet or setting up one more Earth because we are already destroying our Earth. That's so, really bad. No, yeah. So I was actually under the impression that we are planning to figure out a new place for us to live. But the defense related things
I think that's a very good eye opener for us and for the viewers.
I know there's a lot of things that you can do. Like for example, people say they have sent the Hubble telescope. Correct. Up in the sky, and then to look at all. But to flip a switch, it can actually be looking at the Earth. Correct. Correct. And it can be used for other purposes that you don't even know. Correct. Very true. Very true. So that can be a double-edged sword. Okay. So when I was in Goa, LIGO actually, and we had this issue with North Korea. So there were people from the CIA who came and wanted to see if we could actually measure the color degree in North Korea using LIGO. So people can come up with wild imaginations. And then scientists being scientists said we are not going to enter into that that area at all. Mm-hmm. This is built for science, but we do science only. Correct. So that's how it's comes along. I think we're getting into more controversy. Yeah, let's get into the topic. So that brings me to the second question. The second question goes like this. What is LIGO? How does it work? And what can we see through it? I think you already I have answered that question. LIGO, let me in the full form of LIGO. Mm-hmm. LIGO stands for Laser Interferometer Gravitational Observatory. Mm-hmm. The idea behind that is there is a gravitational wave in space that is generated when there is a supernova collision or there is a merger of two binary stars that are rotating with each other because of mass. Okay. And then they collide. So they generate a wave, and that wave comes to hits to the Earth that creates some kind of compression in one direction and elongation in one direction. Correct. And by using this laser interferometer gravitational observatory, we are trying to measure that elongation. Okay. Which is almost at the range of 10 to the power minus 21 meters. Now, I have this common question which people ask. Okay. So, why are we so bothered to observe or to invest more money at an object which we can't even see through our naked eye? It's somewhere science is also helping society in a different way. Okay. The technologies that are developed for doing these things are really state of the art. Nobody has ever done that. And by using that, somehow, somewhere, the technology is transferred to do something else that helps the society. Okay. And that is always something that brings in the connection to the society and the environment. Okay. Okay. I think we are getting saying that we are not audible enough. Is a possibility? Can you bring the mic closer? Okay, without so that. Apart from that, is there any other questions? No. Okay. So telling that, let's move to the third question. Third and the fourth question, rather. The third and the fourth question are quite similar. Can you tell us about your involvement or work in LIGO, which you already did? Okay. One thing I need to mention here is, fortunately, it was myself and my brother who both worked in LIGO. Oh, I was electronics engineer, and fortunately, he also was mechanical engineer. But we both worked at different places. Okay. I was in LIGO Livingston in Louisiana, and my brother was in Washington State in northern, northwestern, northwestern part of US. Okay, okay. So interestingly, both were there same time. Oh, different places. Okay. Working with LIGO. Mm-hmm. LIGO was an interesting thing. Working with these guys. When did you start working at LIGO? In the year 2000. Oh, okay. So when LIGO Livingston was just getting started, okay, the civil work was completed, and all the electronics and the control systems were to go in. Okay. And one of the requirements of LIGO was that we will have a 99.999% redundancy. Okay. The uptime has to be at that level. Okay. There is no shutdown at all. Oh, okay. Once they run, the idea was we will put this machine on, this big huge machine turn on, and it will run continuously for a year. And that was what they would call it as a science run. And in the year, they collect all the data, and all this data goes into various people in different universities who are there, people who mine the data. And there's a very big group in LIGO that does just data mining. Okay. And they're from different universities. There's a people about thousand physicists who are just interested in data. Okay. And they are interested to mine the data and figure out whether there was a signal from space. Okay. And they came up with an idea to use computers that are all lying in various universities or in homes, so you could actually download an app. Okay. And run a piece of that program, and they could get back the result to them. I think a similar program was done by SETI also. SETI also, yeah. Yes. Based on SETI, they adopted this. Okay. And there's also signals from seismometers. Mm-hmm. There's signals from vibration sensors. There's signals from various other inputs that come in to veto out signals that are local to the laboratory or surrounding places. Okay. Did you okay? When we are talking about SETI, I think that most of the viewers will be knowing. Let me elaborate. SETI was a program which was initiated again in collaboration of multiple nations. It was searching for extraterrestrial intelligence. So it was actually multiple computers were required, and when we were actually, in fact, I gave my computer time, most of my computer time towards SETI program. And the fun fact was a blow of a whistle actually triggered SETI is what I had heard, which was a neighboring disturbance, which people thought it is a signal from the outside. So, did LIGO also had a similar kind of? Yeah, as I mentioned to you earlier, a flushing of a toilet would trigger some signal. Correct. But then we had to veto that out. Okay. By knowing that we were measuring that signal somehow, whether by a vibration sensor or a seismometer or something that could measure the local signal vibration. Okay. The interesting thing that when LIGO is situated so far away in a wetland in Louisiana, and it was constructed in such a way it would be like a barge. Okay. And so it would dampen the vibration from outside. Okay. But at the entrance of the LIGO gate, there was a cattle guard where cattle shouldn't come inside. And so they had these pipes in parallel. Okay. And where car could go over it. And the moment car would go over it, we would get a signal there. Okay. And so we would, to figure that out, we had a camera. Okay. Somebody sitting in the control room identified that this signal would go up every time a car would pass over it. And that was one way to veto it. That was a visual way to veto it. Okay. Otherwise, we wouldn't know where the signal was coming from. Okay. And I think probably that is one of the reasons why we started to build an international space station to avoid the surrounding disturbances. There's an interesting thing about even there's a plan or a proposal for building an interferometer in the space. Okay. It's a space interferometer. JPL Jet Propulsion Lab is working on it. Okay. But they've already sent the Hubble telescope, which is doing a wonderful job of sending us all these pictures and all. But they've already come up with the proposal, the costing, and all that. So in the future, maybe we'll see a space interferometer with hundreds of kilometers of spacing between the telescopes, and that will combine light and then will give you much more resolution into uh, the idea of this space and universe and what's up there. Okay. One of the interesting to see, we have only so much limited depth and the resolution that we have. Correct. We see one small light. It could be two lights sitting right next to each other or one behind one another. We don't have that resolution yet to space that out. Space it out, correct. And then we have named it as some name is given to that part of that. So the more we understand, we can say that maybe there are two actual stars very close to each other, okay, are separated by depth or separated by space. So all these things will come up in the future, and that is being funded right now. Okay. I think the similar kind of a technology is also being used to identify the exoplanets also, if I'm not wrong. Exoplanets, I think the next major thing that's going to happen. Okay. Ray Weiss, the current Nobel Prize winner, correct, was on the board of scientific advisors and I think overall they guide where the science goes. They have so much amount of money. Correct. And so everybody can't be given, the proposals can't be. On the top level, they decide what should be the next 20 years. They drive the science path. Correct. With the amount of money available. So exoplanets is surely up there for that. Eventually, whichever subject that you choose trickles down to the
financial education,
Financial
which is very
yes, I
important.
know. Financially, the decisions are made in such a way that they drive the path for science.
Okay. Now, the next question goes like this. What are the parameters goes behind setting up the biggest optical telescope in the world?
What parameters?
Yes. Is it the geographical location, or why exactly was a particular place chosen to set up your
Like for
LIGO station?
example, one of the telescope's requirement is that they want a complete dark sky.
Okay.
But staying close to a big city like Bangalore or any other, it's not a good thing for a telescope. They want like to, so they try to keep moving farther and farther into forests or higher mountains, but light pollution is still an issue.
Correct.
And that is one thing where people have been trying to get governments to say that they have to put caps on the light so that the light comes only down and doesn't go up.
I think in New York they had this umbrella kind of a street light where only the light flashed to the ground, and even the intensity of the light was also reduced. Okay.
Something like that. But
Okay.
now, uh,
But since we are moving from optical to infrared and the other wavelengths, does it really necessary for us to go out? Of course, the flushing of
advantages and the disadvantage, the pros and cons are there. Even optical is very good in certain things.
Okay.
Infrared is good in certain areas.
Okay.
So it's not that you can leave one and then do the other.
Okay.
So even in gravitational wave observatory, when they were detecting supernova, they were always comparing it with as the radio telescope seen it. Okay. As it observed something, can it correlate? So when all these things come, you need all these different technologies to veto out false signals.
False signals. Yes. Okay. So basically, if it is detected in the optics first, then it is double checked with the other wavelengths also. They
check and then see if something is seen, at least
matches.
some signal is seen. If it not, it might be maybe the intensity of that signal may be good in one compared to the other. Then yes, so that's why multiple technologies are.
Oh, okay.
So
nice. That's a nice. Okay. Now the second question goes like this. What is the interferometry telescopes observatory? What is an interferometry? Okay.
So see, we should not confuse this as like an optical telescope. Okay. So if somebody wants to know more about it, there are interferometer telescopes that are coming up all around the world. India also is planning on one called Indigo, and it's still in the nascent stage. But LIGO is the largest interferometer telescope. Earlier, one person named Ron Denver, uh, he built a very small interferometer telescope which could fit in a room, okay, which was about 5 meter long by 5 meter long or so. That's how it started in my mind. Okay. And then Germany has one which is called LIGO. Okay. And then there are other interferometer telescopes around the world. LIGO was the biggest one.
I think we have one coming up in India also, somewhere near Pune.
There's one called Indigo, which people are initially it was named something LIGO India.
LIGO India, yeah.
But I think now they're probably going to call it as Indigo or something. And then Indian Raman Research Institute people from that, IUCA, and all are getting involved to build this thing. LIGO is going to support that. They would like to have a third observatory which can veto and provide confirmation of what they have observed.
I think rather than having one huge facility at one place, how is this? Okay, now rather than having one huge facility at one geographical location, divide the same unit into multiple smaller facilities and spread across the.
It's not dividing the facility into smaller units. It's replicating the same unit at different locations on the Earth. Okay. Because then you can, as the Earth rotates, if you say the same signal from outer space on your other interferometer, which is in India, and same correlates with what is in US when it's facing that object. Okay. Then you can be sure that it's coming from outer space.
Basically, having in contact or observing the
Same object
throughout the rotation of the Earth.
rotation of the Earth, and so people prefer that to ensure that there is some authenticity to this thing instead of observing and being able to only replicate it only one place.
So basically, to avoid even the intervals which is caused because of the rotation
of the Earth.
rotation of the Earth. So you mean to say that if you take the globe and they divided it into three equal locations and placed it like that, or how
Not
exactly?
It depended on the country which was ready to fund it.
Okay.
So, but you know the distance and the arc seconds are different apart.
Okay.
So based on the Earth's rotation speed, you know at what time difference the signal, if it appeared in New York, will appear again in London and will appear in Delhi. So you will it appear at the same time difference? We can check that out.
Okay, that's one. Now, the next question goes like this: what is the current state of telescopes?
Oh,
I think this question.
This what I've answered that. I think there's a lot of competition in the telescope.
Correct.
India itself is trying to get a bigger 2.4-meter telescope installed in.
I think
In the Himalayan.
Himalayan, yes.
Yes. And people are looking. We already have a 10-meter diameter telescope.
Leh, in Adelaide.
In Leh, Hawaii. And then the next technology, DMT, where my colleague Gary Sanders is the project manager. They want to build a 30-meter diameter telescope. So that's the interesting challenge.
Okay.
They were looking at building in Chile all the Andes one because the air is so clear. But they ran into various things. I think now they have decided to build it in Hawaii.
Okay.
Because I think there was also issues with funding being taken out of US and things like that.
Okay.
Then Europe said we are going to build one more thing, which GMT where they were building, which is a 24.4 or 25-meter diameter telescope.
Okay.
And I think the European nations came to this and will build much better. They did the extremely large telescope, which is a 42-meter diameter telescope.
So it's like a race. Who
Yes,
has the
who has
bigger,
the better and the
who
best
has the bigger and
toy?
the better.
It becomes who has the best toy in the world so to play. But interestingly, all of these things, like India can pitch in with some amount and say we are going to share some cost. So they get a time share, which they can go use, and all the data that is there is available if they become a partner. So that's where they do, even if they don't have to build it, they can at least get share in that.
Now, talking about the shares and the data and accessing of the data and getting the answers or whatever the solutions of the data. Now, if we look at the moon missions, there were a handful of moon missions which man went and did. We got the samples, and we have LRO, which is giving continuous data to us. And even the Hubble also has terabytes of data which is still not being verified and things. And still we have the hunger for more data. How do you justify that?
Well, data is there, but I think the hunger is there to know more, or explore, and go beyond what we know.
Okay.
Because interesting things are happening around the world, and with people just choosing one star or one object and putting their whole life on it. Okay. Like one person is studying only about the Beetlejuice, and one person is studying about the Lyra.
Correct.
So there's enough people.
Talking about Beetlejuice, I think I'm waiting from almost 10 years now for Beetlejuice to die. It is a sad thing.
Yes,
but
I know. It's still going on.
It's going on.
And it's feeding now number of people who are studying only Beetlejuice all their life and career and writing papers about it.
Correct. In
Interesting.
fact, I think in 2016 or so, the entire world was very eager to see a star die, turning into a supernova and clearing a huge celestial event. So, and that was a bigger buzz. Then we had this comet Ison, which was biggest hype. Now, talking about the hype to the reality, okay, astronomy is one thing which has always been hyped up subject. Okay, whether it is a solar eclipse or whether it is some asteroid which is going to come, or whether it is any celestial event, or the various recent black hole image. Now, how does the common man take astronomy so seriously, or how exactly do they?
I think it's fun for the common man to say, oh, wow, there's something happening upstairs that I'm not privy to, or that is above our purview of things around us.
Okay.
And yet it's happening up there, and we're able to see it, and those astronomers are able to point out to us.
Okay.
And it's interesting that way for the common man.
Okay.
But for the astronomers, I think it's a lot of things that they can actually study about and then able to explain it to the common man and say this is what's happening up there.
Okay.
And this is where in some of the images they can actually show what's how the universe is. And the recent somebody had posted a picture of the Milky Way, and that was an interesting thing for somebody to say, oh wow, it's really like this. And in recent days, I see most of the people are investing in telescopes. Most of them don't even know which telescope to choose and other things. And they feel that I get most of the requests saying that I wanted to see the Saturn like I see in Google. Yeah. So I keep telling them that what is shown in the desktop and what you see through the eyepiece is a totally different thing. Yeah. Okay, you get a when I say magnification, you won't get a full HD image of view through the telescope. Now, telling this, what are the parameters do you think like a layman should think or should consider before buying or investing in a telescope? If I wish to have a telescope in my backyard, okay, what do you think, or where should I or no, you should probably first see what is it that interests you. Are you interested only in looking at the moon, but are you interested also looking at Jupiter and Saturn and the power of planets? Like at what size and what image, what density, okay, and like what clarity. Okay. Yes. So magnitude comes into picture, and magnification comes into picture, resolving power comes into picture. So, but then, as you said, the more you go, the cost becomes higher and higher. So whether you can really afford it, and is it worth for you to, like, what will you do after you have seen it? Correct. So unless you're somebody who's really going to pursue into this and actually have fun of it. In fact, I always keep debating astronomy need not always be done through telescope. There is 101 things that you can do astronomy without a telescope. I think we also ran couple of seminars and talks called as astronomy without telescopes. It was quite interesting. We had thousands of viewers also. Wonderful. Okay, so that is one thing. So you can actually go out and just by the naked eye look at all the constellations. And if you know the names of them, and then actually, it's a fun way to. It's a very fun way. I think people who are within the Bangalore, we rarely get to see a clear sky, and we being in South India, we're always jinxed with the clear skies. Now that brings to the last. Can you talk a bit about your colleagues who won this year's Nobel Prize in Physics and your experience with them? Interesting guys. I had much more closer interaction with Rainer Weiss, or we used to call him Ray. Okay. He was an hands-on guy from MIT, a professor from MIT. He would come and actually work with things hands-on. And never in their mind, I think, like they would think that, oh, we are going to win a Nobel Prize at one time. The aim was always like, let's just work. Let's get through this, let's build this thing. And goal was not to get a Nobel Prize. Okay. Kip Thorne, the guy was a theoretical physicist, astrophysicist. And he was always in Caltech in my. I had little but few, some interaction with him. Um, but none of these guys are like, if you say modest, humble, they'll sit down, do their work, whatever they want to get done, and then uh, spend all their time with the work in the environment, encouraging people to do this. But before they even got to build LIGO, they spent all their life doing other things before the money came to build LIGO. Okay. And they had to prove that they could build this and something will come out of it. Okay. Now they have gone to advanced LIGO stage after the first phase of LIGO, where they were able to detect supernova explosion on one event. And now they say in a year maybe they can detect about 10 events or so. Okay. So that's a big change for them. So yeah, at least one event a month is good for somebody to use it for some study, some thesis, some. So more PhDs can come out of this together. So I think it's a very unique transition from being an engineer. I think you studied engineering in RV College, right? Yes, I did my engineering in electronics engineering from RV College. Okay. And then I had no inclination to go into astronomy. So even there, I was more of an electronics controls engineer. Okay. But then gotten into some astronomy because colleagues were all people who were. I think you had more gravitational effect towards astronomy than the electronics. And then I gotten into after 5 years at LIGO. Okay. Uh, the scientists, the physicists came in. They said we are going to do a 1 year science lab. All engineers hands off, don't do anything. We'll keep this running for because we had proven that this could run at 99.999% uptime and no failure. Okay. And for 3 years, 2 3 years we had done that. So fifth year they decided, sixth year decided we will do this. Okay. That's when I thought this time I should go to something else. Okay. Instead of sitting there and just doing repairs and things like that. Then I moved to Magdalena Ridge Observatory. Okay. Where they were building the fast tracking telescope and the Magdalena Ridge Interferometer. Okay. So, as a lead electronics engineer, I was involved in designing all the electronics and the control systems for each of these telescopes. And the interesting thing of this was you had to pick up telescope and move to a different baseline as and when required. And so you had to have a telescope on a trolley. Okay. With also the dome and everything movable. Okay. And with the effects of hot air coming in the morning and then the cool air in the night. Okay. The differences in that way to make sure that the telescope doesn't expand and contract and all that. So interesting challenges that we face. But finally, I think the one or two telescopes have come in. Okay. Out of the 10 we had planned again. Remaining are getting manufactured in Belgium. Okay. And once they all come in, I think it will be interesting to see what Magdalena Ridge Interferometer detects. Okay. But otherwise, the fast tracking telescope is being used for other purposes other than astronomy also. So no, we know. Okay. Now coming to the end of the talk. Okay. For example, for the youngsters to get into this profession, what do you suggest them to have in their degree, or how exactly do they have to plan their career to move towards this kind of a research or to move towards this kind of a field? I'm interested in astronomy and then physics mainly. Okay. So branch of physics deviates into quantum physics, astrophysics, and various other things. So if you're interested in astrophysics, you can get into astrophysics, and then once you're into astrophysics, you can decide to be whether you want to be a theorist or an experimentalist. Okay. If you're a theorist, there are a lot of options where you theorize about something, and then the experimentalists have to come and actually prove that. So then there you build up all these telescopes or observatories, such and such. So as there are people who are also interested in instrumentation, who go and develop cameras and imaging instruments and things like that that can be used in this telescope. So there's a wide range of options, whether it's an engineer or a physicist who wants to get into astronomy. Okay. I think even a good cook can go to a space. Yeah. Is what I think. I think if we had a chef who can compact and who can prepare a dish which can survive for a long time, also can be an astronaut at one given point of time. Anybody can go to space, I think so, if they're interested. Okay. And more, I think space operations will come into play. Okay. With all the other commercial players coming into play. So I think by a few years, space travel will become something like that you do for fun. Okay. And then I
I think a school trip or an educational tour can be for a space.
Space, and then they experience the effects of space and then come back.
Correct.
And in the future also holds good for exoplanets, and then maybe Planck's equation. Correct. Shows that the possibility
Of life
of life in another planet is much better than the probability of winning a lottery ticket.
Okay.
So that's much good. So hopefully, I don't know, but they're also interesting that sociologists in other places are also looking at it and saying, what if we do find a planet with people or some other living beings? What
Okay.
will we do?
Correct.
And how will we behave? What will be our relationship? And how do we react? And all this. So there are all these other people also who are looking into it. It's not only the astronomers.
Correct.
That who are interested in outer space.
I think it's quite fun to, if you look at our surroundings, we have people who still, we have a huge community rather than people. We have a huge community who still believe in flat earth, who say earth is flat, and we have a community which says that, okay, now we are done with the earth, now let's go settle in Mars. Then we have one more set of community who invest huge amount of money saying that let's forget solar system, let's go and find one more system. I think this transition of, or rather this evolution in astronomy, I think is given huge wide spectrum like how we have in the EVM. So coming to this, where do we stand? We as an Indian, where do we stand in this league of evolution in astronomy?
I think that India, as far as now, is lagging behind in terms of astronomy, which is not open and not publicly uh, like public awareness about the existing telescopes, where they can find it, whether there's a class excursion or a tour or public viewing which can go visit certain telescopes and understand about what's happening in astronomy and where India stands is still needs to be improved.
But if I'm not wrong, I think Venubapa Observatory and the Hanley telescopes, okay, were the first to discover. In fact, the Venubapa Observatory was the first to discover the Uranus rings, if I'm not wrong, and later on it was verified by the other universities in the US. So, though we had set huge milestones, and if you go back to our archaeology and if you look at any of our big temples or the monuments, we can actually say that we were somewhere else, but now we are still here. We don't know where exactly is the dot which is missing between the two dots. Okay, the three dots. Now, how do we actually go back and connect the dots and link it back to our ancient knowledges?
There is there was some very good knowledge and technology, even technology for that time in both the temples like 11, 12, where you have seen rocks that are carved, that are turned to such smoothness and precision that we see in grinding machines today.
Correct.
And also we've had this notion about the nine planets, and but the nine planets, if you look at Surya, Chandraya, Budaya. So Surya, Chandra also were included as planets. But so where there was some, I don't know whether they thought that Sun and Moon itself were also planets, or they included them as part of the nine planets and stuff. But
I think we have to find the dot which is missing in the center. Yes. One, or we don't know. There is one dot or a series of dots.
So somewhere along this line, we have somehow lost the link. Okay. I think the link should be traced in things like Nalanda University that we had is lost.
Correct.
Maybe they could have been our explanation. I don't know, somewhere where we lost.